says the differential is f prime dx. Okay, that's all it says. When I do example A, if I follow the theorem, then this differential y is y prime dx. I just have to find the derivative of x to the fifth plus 2x. That's all I have to do. I said f prime of x. So the derivative of x to the fifth plus 2x, okay, we'll do that off the side, is 5x to the fourth plus 2. I actually should have wrote y prime of x here. They want that 1 in there. So the theorem says f prime of x, plug it in. All right, so the differential for y here is going to be a 5 times a 1 to the fourth power plus 2, and all of it getting multiplied by the change in x. See how that's in the theorem? dx. This goes here. And it's the whole thing, too. There's two pieces here. That's 1 and 1. So 5 times 1 to the fourth, I believe is 5. Add 2 is 7. And you're taking 100th of 7, which means you shift the decimal 100 places. Take 100th of number, how many places you shift the decimal? 2. So what is 100th of 7? 107, 7 hundredths. How do you want to say it? Oh, that's all good and well. What does that mean? It means if x increments or changes, whatever word you like, or increases by 0.01, y increments by 0.07. I wish the book didn't use the word evaluate here. It should actually estimate. It's an estimation technique. Again, this goes back to before technology. So, if you want to know how much something increments by a 10 or maybe 100 thousandths, what happens? You don't really want to plug in like 0.000001 into an equation. Now when you got to cube the thing or square the thing, it takes a little bit of time. So it goes back to just estimation techniques and making things easier because they're still highly accurate, which was good enough in World War II. Let's see here. Let's do C. B looks like the same exact type of problem. C looks a little bit different. One, I'm pretty sure that I see implicit differentiation. I don't know. I'm going to look at it. So again, we got our simple theorem here. dy is f prime of x dx. What's dx? 0.05. Okay, that's going to go there. And we're going to let this x, be there. I can find the derivative. So let's find the derivative. We can call it y prime, f prime, I don't care. Well, I wonder if there's an easier way around this thing. Is there a way to avoid implicit differentiation? I think there is a way to avoid implicit differentiation. Or would you rather do implicit differentiation? No? Elizabeth, do you want to see implicit?
Yeah, I need to, because I don't know how it works.
Okay, so Elizabeth needs to see it. So we'll do it. Now, how about I do both?
That sounds good. I like that.
What we do, first we do without. Pretty sure I can get away with it. So if I want to do without, what I want to do is I want to solve for y. I want the equation in y. All I want. So y is on one side, x is on the other. And follow your first amendment. Well, I teach you so you can pull it for it. What can you pull out of the left? Negative x, thank you. You can pull the y out, can't you? And then you can do a little division. And this will save you a little bit of a hassle in that you will not have to do implicit differentiation. But you will have to follow what rule? quotient rule. Not a huge deal. That probably would be, Tanner, you got the quotient rule backwards on your quiz. I remember that. Bottom piece times the derivative of the top minus the top piece times the derivative of the bottom, sitting over the bottom squared. You did, you had those two backwards. You had them in the wrong place. Got the sign on because turns out you forgot another sign in there, so you end up with the right intermediate work because of the two sign mistakes. Sometimes two wrongs doesn't make a right. That's what they tell you. Two wrongs doesn't make a right. That's a lie. Sometimes it does. No, I take off points. All right, what's that going to clean up to look like? Well, the -1 plus x. There's going to be a lot of cancellations, aren't there? It's too tired to see it. That's -x, isn't it? It's a negative times a negative times a negative. I guess that's 2x minus 1. That's how you do it without.
Is that negative on the answer? Yeah. And then what you just had, -1 on top.
Yes, that's exactly what you have. Showed it there and then I forgot that I wrote it. All right, so for Elizabeth, let's do this with implicit. So we get the same thing. I'm having one of those days though. Freaking kid woke up at 4:30 this morning. What a jerk. And then he proceeded to talk, he'd be sweet, until about 5:50. Which is not as cute as it sounds. It's not cute. You're sleeping. What's wrong? Anyways, with implicit. The deal with implicit is every time you take a derivative of y, what do you write? I mean, if you like, you can use y prime. You really can. It's up to you. I like to do y dx. So the derivative of x is 1. The derivative of y is dy dx. On the right hand side, you got to use a product rule. So you have an x dy dx plus y times the 1. And it's going to be, from here, probably the same as we did the last time. Everything with a dy dx on one side and everything else on the other. All right, so I guess I'll shift, doesn't matter. I'll shift dy to the right. On the right side, I'd have 1 minus y, which I'm going to have to do something with. You can't have y back in itself. I'm probably going to have to go back and look at some work that I erased. Didn't I solve for y earlier? This is kind of a pain in the butt, I don't know, it really is. I guess we'll pull the dy dx from the right-hand side. That's going to give me an x minus a 1. Divide it out. Now, what is actually wrong with that equation? Like, why can't I use it? It's referring to itself. The derivative of it is referring back to itself. That's its issue. It needs to be written in terms of x's. I have no idea what I wrote earlier when we solved for y. What did I write when we solved for y? I'm going to go right there. 1 minus negative x over 1 minus x, sitting over x minus 1. Well, it just got even harder. And I have to make sure that it cleans up to be what we had before, which is even more fun. So I have a hunch that one of them's wrong, but we'll see. So I see minus a negative, that may as well be plus a positive. Don't you have to put those fractions together? You have 1 over 1 plus x over 1 minus x. What do you have to give the 1? You have to give it the 1 minus x. 1 times 1 minus x plus x. You know, the unified denominator of 1 minus x. Kind of interesting. Sitting over x minus 1. All right, so that numerator, hey, we got kind of lucky. 1 times 1 minus x plus x is just what? 1. This doesn't look like our answer, does it? What was our answer before? It was negative 1 over x minus 1 squared, right? We can get there. How do you get there? I can make 2 routes over to there. How do I get there? 1 minus x looks a lot like x minus 1. How could you make 1 minus x look like x minus 1? Pull the negative. Pull the negative, put the negative up top. Where does division happen? Oh, so you just shift this guy down there. That makes it x minus 1 what? Third. How about that? You're right both ways. I have no idea which way is going to be easier for you to do. Riley, you probably have a third technique. All right, so all that for that little bitty answer. Oh, cool. I've already got that. This is for me. I can't keep up with anything today. I'm just borrowing stuff. There we go. So, what do we have to plug into that thing? We have to plug in a 2 and we have to multiply it by what? 0.05. That's how you find the differential in y or the change in y. And it's a good idea when you start seeing things like this, when you start seeing dx, you know, you can read it to yourself as dx, but be thinking change in x. When you see dy, change in y. No, that's another alternate way of reading. Kind of like when you hear the word derivative, you think slope, right? You think tangent. Those are the things that pop in your head. Do you understand that? So put that in your list of things that pops in your head when you see it. It goes back to like algebra 2. You've got a whole bunch of kids who understand what a zero is, but then they don't know what a root is. Or they don't know what an x-intercept is. Aren't those all the same thing? You know, when you hear one of them, you think of the other. It's kind of like the source. Everything's the same meaning. Anyways, dy here is going to be a -1 over 2 minus a 1 squared times 0.05. It shouldn't be too hard. What do we got? I think we just have -0.05, don't we? I wrote, is it? Okay. I shouldn't have given the bottom. Does it matter? I can't do that. We can see.
You just wrote the same thing on one. When you took the negative out, you should have made it 1 minus x. Yeah. You're using a mistake.
I'm surprised that matters. That's what I'm surprised about, that it's actually making a difference. So our original derivative had 1 minus x down there. So I should have negated this guy, made him 1 minus x. I'm just kind of shocked that it's actually making a difference, because it's same. Or I screwed up some, I don't know. There shouldn't be a difference between 1 minus x all squared and x minus 1 all squared. Apparently, there is in this problem. This is what I'm saying, it's the same thing. There's no difference between 1 minus x and x minus 1 squared. As I was saying, it doesn't matter. You see that doesn't matter? You get the same thing out of the way. Both generate the positive 1. You have -1 over 1, which is -1 times 0.05. -0.05. So if x increases by 500ths, we estimate that y decreases by 500ths. And that's the beginning of differentials. The next section of your book is all about differentials. This is just kind of a warm-up to it. I don't even know why they put this in your book. It's the same exact theorem. Huh? No, I gave you homework problems. If I don't put them there, you're going to ask about it. Probably still will. But let f of x be differentiable at x equals a some point. The approximate change in the value of f when x changes from a to a plus dx is f prime of a dx. When it talks about find the differential here, your book has some kind of weird things, like they put a little d out front. That d there is standing for differential, or in other words, find the derivative and include dx. That's all the theorem is telling you to do. So what you're going to do is you're going to take the derivative, and when you're done taking the derivative, you're going to write dx. Okay? So when you see that d, take the derivative. When finished, include dx. It's all the theorem is wanting you to do. It's kind of like when you take the derivative of y. You say dy, don't you? Well, here you're taking the derivative of a function of x, so you state that you're taking the derivative function of x by saying dx. So d tan 2x is even new. It's actually saying take the derivative of tan 2x.
I meant to go back and edit this thing and put a set of parentheses right there, but I didn't do it. That's what I got to do, I just forgot to do it. So, what is the derivative of the tangent of 2x? This is why you need a formula for this. There's a handful of y'all that forgot that on your quiz. If the argument of what you're taking the derivative of is somewhat complex, more than just x, you've got to take its derivative as well. It's a chain rule. And we're going to include dx because we did take the derivative of a function of x, and we'll rewrite that to be 2 secant squareds twice x dx. And if you see anything in your homework or on the quiz, it just says d. That's what it means you do. You take the derivative and you add dx. We're building up for something here because what's up next is called anti-differentiation.
So everyone who takes it either have the dWs or the dx?
Pretty much.
Okay.
They're starting to build you into the opposite way around, anti-differentiation known as integration. And you need that piece there. What's wrong? If you know how to take derivatives, it's easy. If you struggle with taking derivatives, yeah, it's darn near impossible. In your past classes, I've given a lot more formula quizzes. I really need to start it up here. All right, so the radius of a circle increases from 5 meters to 5.1 meters. Use dA to estimate the increase in the circle's area A. And notice it's an estimate. These are estimates. Now, when you see dA, that means derivative of A. And A is simply a reference to the circle's area. So first off, how do you find the area of a circle? R squared. What would dA be? The derivative of A. 2 pi r. Now, if this was a function of x, we would include x. This is a function of r. dr. What's that dr mean to you? Change radius. And yes, it means you took the derivative of r as well. But in this particular problem, it is talking to a reference in change in radius. All right, so we're supposed to use dA to estimate the increase in the circle's area. What was the change in radius? 0.1. The R is 5.1 minus 5, which is 1/10. So the estimate, dA of 0.1, is twice pi times 0.1, which is 0.2 pi. It's actually really close. It is. The actual area is going to be pi times 5.1 squared, which is, I don't remember off the top of my head, 26.015. What's going on? I did this yesterday and I got 26 pi.
Did we forget an R?
Yes, we forgot an R. I did. You didn't.
Well, we got
You didn't forget anything.
I was like,
Well, I just found it. What am I supposed to plug into the R? 5.
Not 5.1, 5. Because it changes on the last part. Okay. Anyways, that's pi. That means that the circle's area increases by pi units. Okay. So the estimate is the original circle of 25 pi plus pi, 26 pi. That's the estimate. We estimate that we'll have area 26 pi, square inches, centimeters, wherever this thing is written in, compared to the actuality of 26.01 pi. And 5.1 is not a hard number to work with. And again, they weren't working with numbers like 5.1. They were working with crazy little decimals. Okay? Teeny tiny little things. So they used estimation techniques because they're very highly accurate. That's pretty close, isn't it? If you go back to the original circles area, pi r squared, 25 pi. So again, it was just to get things very, very close. Didn't have to be perfect. What's up next? Bicycle tire? Inflating a bicycle tire changes radius from 12 to 13 inches. Use differentials to estimate the absolute change, the relative change, and the percentage change. Now, when I read the text, the very first thing I notice is the change in the radius. What is it? 12 to 13. What happened to the radius? Grew by 1. Okay. Now we're going to use the original radius. It's 12. Okay. Whenever we use our formula, we're going to use the original radius 12. We already have a formula too, because we just did it on the previous slide. The differential of the area, or the change in the area, was 2 pi r dr. Wasn't it? No. What's this question about? Perimeter. They use the word perimeter. Perimeter, which is better known as circumference, is what? 2 pi r. So we're not going to find dA, we're going to find dC or dP. So change in circumference would be the derivative of 2 pi r. What's the derivative of 2 pi r? 2 pi with respect to r. 2 pi dr. No, I actually don't need to know what the original radius is. I don't care what the original radius is. All I need to know is what dr is. 1. So change in the radius when the radius is increased by 1 is simply 2 pi times 1, which is 2 pi. Now, we would say that our absolute change, or our estimate here, is the original plus 2 pi. Now, the original circumference of that tire is 2 pi times what? Times what? 2 pi times 12 plus 2 pi. We estimate that it's 26 pi inches around the tire. That's an estimate. Huh?
What are the other arguments? It's 2 pi r. And then you have the dr. Oh, no.
Took the derivative of circumference. There. So that's what we estimate the tire to actually be. Now we are supposed to estimate the absolute change, relative change, and the percentage change in the perimeter of the tire. So the absolute change is actually 2 pi. We gain 2 pi. Relative change, I'm going to check with you both, make sure I'm writing this down again. Because there's a formula that makes this really handy in more complex problems. That's what I want to make sure I get in here, right? Because we'll kind of want this formula for the next example we do.
Your relative change is going to be df over the original. By the way, this little piece here was the absolute change. I'm going to write these down. Absolute, this guy is going to be dr, change in r. I just need to insert a new slide on this one. Now I'll go back to it. All right, so you have some function, dy equals f prime of x dx. Absolute change is f prime of x dx. That's the absolute change. That's the estimate. Relative change is f prime of x dx sitting over the original f of x. Then you have percentage, which is relative times 100. I was trying to figure out how to teach that without actually writing this stuff down. I think it's best if you just have that written down. Now we found the absolute change, it's 2 pi. We found the estimate of the absolute change. What we're going to do for the relative change is we're going to put that 2 pi over the original. So it's over the original. That was area, circumference. You're having the same issue I am today. You're somewhere else. You are. You're not talking about true change, you're talking about relative. Absolute is 2 pi. Relative is this 2 pi. Notice how your formula says over f of x, right? Well, what number did we plug in here? We got to use the same number there. It was f prime of x over f of x. You have to use the same exact number. Over circumference, which was 2 pi times 12. It does turn out to be 24, Jim. You get 2 pi over 24 pi, which is 1/12. Everything's set up. As a decimal, that's really, really close to 0.08. I don't remember what's after the 0.08. Probably a 3. It is. It's a 3 that goes on for the rest of its life. 0.083 for the rest of its life. That's the relative change, 0.083. Huh?
So we just multiply that by 100.
Yeah, to get the percentage change, just multiply that by 100. 0.083 times 100 is 8.3%. And those are estimated changes. Okay, that's not the absolute. It's not, sorry, it's not what really happened. It's not the exact. Now, the reason I want to talk about that here was for your next example. So here's some French dude in the 1830s. 1830s was about 100 years or so after calculus was created. So we started using it. The formula we use today to predict how much the radius of a partially clogged artery has to be expanded to restore normal flow. He came up with this formula on his own. Volume is some constant times r to the 4th. That's a pretty big deal. It is. You may not realize that, but that's a big deal. My dad had a heart attack. I'm sure they had to expand a couple of his remaining arteries. I'm sure lots of y'all have known some people with heart problems. Sometimes they have to do this. So it's a pretty big deal to restore normal flow. They'll put a stent in or something, make it wider, get you back to normal. All right, it says the volume V of fluid flowing through a small pipe or tube in a unit of time at a fixed pressure is a constant times the fourth power of the tube's radius. How will a 10% increase in the radius affect the volume? So we're going to have to go back and kind of use those formulas that we used. First off, we're going to find dV. By the way, we do know dr, don't we? What's dr? dr is 10%, better known as 0.1. Now dV would be the derivative of this thing. K is a constant, okay? So it's like the number 3 out front. Where's the 4 go? Pretend K is a 3. Where's the 4 go? Out front, right? Still goes out front. 4KR, what happens to the power law? Increases, and then we say dr. Now we're going to plug in that 0.1. Right. And we'll just simplify it. 10 to the 4 is 4/10. Now, they want us to figure out how much a 10% increase in R affects V. Look at your formula for relative change. Isn't relative f prime of x dx over f of x? Isn't that what you wrote down? Well, you know what f prime of x is. You just did it. You don't have a number like you usually do. You have it, don't you? It says 0.4 k r cubed, sitting over the original function, kr to the fourth. Now, a whole bunch of stuff disappears. A whole bunch of stuff disappears. The k's are gone. R cubed's gone. There's an r down. So this is 0.4 sitting over r. Now, there's a unit I'm missing here. I forgot to put a unit. I guess I'll mention it. This 0.1 was actually 0.1 dr. So that's 0.4 dr. Wasn't that 0.1 the change in radius? That was his actual unit. It was 0.1 dr. And I just forgot to put it in the text. See how I wrote this? I think I just did that. I was supposed to say 0.1 dr. Now let me shrink this up and try and explain this. Units are one of those things that people gloss over a lot. And I guess maybe I should push it harder. The truth is, I don't like them in the first place either, which is why I don't. When I read 0.4 dr, it is read 0.4, how do I read that? Is read maybe better as a fraction, maybe? The change in volume. Well, let me talk about dr over r. dr over r is read change in r with respect to r. I'm still missing something. What do we have on the right-hand side of this? We had change in volume, right? dV is equal to 0.4 R dr over R. I really don't know the best way to explain this. This means that the volume increases by 40%. I don't know the best way to explain that. I thought I had it down. But apparently I can't put it in words. So as the top increases by 4/10 of a unit with respect to its radius, the volume increases by 40%. Now, anyways, I did finish your notes finally. Sorry I hadn't been a very good teacher today. I have not been a very good teacher today. I'm having a real bad teacher day. But anyways, give your homework a shot. Ask me 20, 30 questions tomorrow. We'll go over them.